Okay, right. So I'm going to fill it up some more. Okay. So let's talk about me first, because that's important, and then we'll go into stuff. So I work for IBM. I don't work for Red Hat. Okay. I work for the Research and Development Lab in the UK. I work on JVMs. That's my primary job, and I've been doing it for a long time. And I'm also a developer advocate, which means I get paid to come out and talk to you guys, which is really cool. Okay. Done lots of stuff, but been doing it for a long time. So this talk is about the futures. It's about some of the stuff that's happening now and some of the stuff that's going to happen. Okay, and it may sound like a technical talk, but it isn't. Okay, it isn't actually a technical talk. Right? This talk is actually about why the future is going to change your brain. Okay, because the future, and it's already here, but the future is more about how you think and what you do more than anything else, okay? So this is more about your future, a possible future, than you might realize, okay? So what do you think about now? What's important today, right? What are you thinking about? You come to this conference, you go to a bunch of sessions, you're learning stuff, okay? You might be thinking positive stuff about Java. You might be thinking about have I learned something new about Java 8? Have I started looking at Java 11? Okay, have I figured out what does LTS mean, and do I have to buy Java from Oracle, or can I get it somewhere else, and what happens, right? Maybe you've even had a go at the module system. Maybe you've been one of the lucky few who've given that a go, right? That's all now, okay? That's all now. Oh, okay, so you can't read the bottom line, but I can. Okay. It's really easy for us to think about now because that's our day job and that's what we do, and it's all about what we need to do now. But it's occasionally a good idea to just look up and think about the future. Think about other things that are going on in the community. What does it mean for EE? Has moved, Oracle is contributing EE to Eclipse. We have this Jakarta EE. Why? What does that mean? Why did IBM open source their JVM? Oh, sorry, I'm IBM. Why did I open source our JVM? And our application servers, Open Liberty. We've put stuff into the open source community. You may have gone, oh, okay. Well, you should think about why. You should think about things like microprofile. Why does microprofile exist? No, I don't have the answers to all of these things. I have some basics. But it is important that you pay attention to what happens in the world around you, because the world is changing, right? Should you be using Spring or Ruby or Go or Rust or whatever, okay? Why do you think, okay? Shall I use Java? Is just Java important? Try to carry on doing it, okay? So the first thing is, what do we think? Oh, okay, it's a picture of a monkey, gorilla, and it says at the bottom, let's think about what drives us. What actually is making all this change? All the things you're learning about at this conference are coming from somewhere. Okay, it's one word. This word, economics. Everything is driven by money. Making things faster saves money. Making things cheaper, easier, better. It's all about money. It all comes down to how do we get more out of what we've got. So the Java community has focused on one thing. For many, many years, the primary innovation has been driven by on performance. Okay? This thing. Moore's Law. Okay? So this chart was created, I think, about 2010, a bit earlier than that, before Moore's Law had a bit of a hiccup. Okay, and these guys put this together. You can, it's just a Wikipedia page, but you can see we had this thing. We can produce every 18 months, we get twice as much power. And all that happened was, as a community, we created solutions that were about exploiting that, making sure that our businesses got best bang for buck. JVMs, could they exploit it? More cores, more processors, more transistors, do that. And then everything on top of that, can we make sure that our app servers can deal with that? And that's been our drive. Okay? And we've been really good. And we've actually built this nice walled garden around it. You all know, if you're a Java programmer, you are probably, if you've been doing it any more than a few years, you will know that Java is like, well, it sits in this JVM box, and it doesn't talk to the outside world. And we made that deliberate choice, because it's really good to optimize stuff that's in a box. But once you're communicating outside the box, it gets really hard to get the benefit. Okay, so we made it really, really good to do enterprise Java. And as a community, we have been spectacular. All the guys out there, all the guys who aren't there, the VM developers, the application framework developers, all of us have worked together to create this fantastic environment. We've collaborated, we've competed, we have the best place. Right? We have the best garbage collectors, we have the best JITs by far from any other runtime. Right? It is fantastic for Java only. We've developed JVMs that can run on the tiny, whiny devices to the really big things. On every architecture you can think of, every OS, we've done that with JVMs. Okay? So how small? So if you've got a credit card and you've got one of those little smart chips, those on there, those MPU things, inside there you can find Java. Not every single one. Java is on the smart card. Java is next to the processor that's on the smart card. Java is embedded in the processor. And the reason that is that, well, if you get 2 grains of sand, you can get 100 million transistors out of 2 grains of sand. So 100 million transistors is enough to put a VM on. And we do this. Why? Why are we doing this? You may not have realized that there is this Java Card VM out there. It's been around for 20 years or more. Okay, maybe a Java space you didn't know of. It's not quite the Java that you know, but they love Java because, well, you imagine trying to debug Java on a smart card. You've just sold 6 billion of them, and then something goes wrong, and you need to get them back. If you don't use Java for that, and you use something else, it could be quite catastrophic. Java's really good for helping you develop applications that are slightly more robust than other languages. Okay, but the point is, these guys have sold into Java at the very tiny end, and then there's Java at the big end. How many of you work for a company that has a mainframe? Oh, that's so many more hands than I'm used to. Thank you. So, mainframes, not your old iron, as it's called, modern computing. 170 CPUs, 32 terabytes of RAM, enormous heaps. It's the latest Z14 from IBM. Point is, Java can do that too. Okay? So cool, small to big, okay? But it's all still been driven by somebody else going, innovation has to happen in your space. We've changed the world, okay? So we dealt with the Moore's Law stuff, and we've got Java that runs all these machines, and we're all okay. And then, of course, what happens? What's the new thing, well, newish, that's been knocking around? Compute on tap. Or, as is better known, cloud. Faster, cheaper, easier, better. Same economics. Economics still rules. It's all about money. As Java developers, you're probably beginning to see something like this happen. New rules of the game. Okay. So, with cloud, you buy things by RAM, don't you? You buy a tier of Amazon. Wherever you go, you spend money and you get compute. So compute equals money. And your accountants understand that. They understand the relationship between the money that you spend and the compute power you get. So actually, they understand this equation. Money equals gigabytes per hour, because that's what we buy. You guys, if you're using cloud, and believe me, if you're not using cloud, you will be, it's all about that equation. That's the primary one. That's the primary economic value that we run to, that equation. So as a Java programmer, it means this. Right? So this is true. You think, if your accountants understand compute equals money, understand this. When you come to them and say, okay, I'm now going to stand up a JVM application or Java application, and I need to go off and make the memory a bit bigger. We've made these changes, we need more memory. They go, that's money. How are you going to pay it back? And those questions are happening now. That's a driver to us, okay? And I said cloud wasn't going away, and it surely isn't going away, because, and here's just an example, because I work for IBM, we have this thing called Cloud Private, which is cloud that you can install locally, okay? Cool, you can clone it and create it as a developer environment. The point is, it looks like this, or variations of this. Businesses are going, I love cloud. I love public cloud. I like the economics. I like the dashboards. I like the control. I like the fact that I can manage things and deploy things so much better than what I have on-prem. So they go, can I have cloud locally, please? So clouds are turning up everywhere. So the economics I'm talking about isn't one that's, oh, it's public cloud. It's all our lives are going to be affected by this, okay? This is a challenge. The challenge is we built this fantastic walled garden that said everything in here is going to run really well for a particular type of environment. So we said small devices to big devices. Nobody ever said anything about cloud. So our challenge is to find a way to break out of the walled garden and adapt and innovate so that we can figure out how to do Java better. Because if we don't do that, somebody else will. And somebody else will come along with a better environment, a better programming language, which we don't want to have happen, because from a vested interest point of view, we have built a fantastic community and we have created VM technologies that are best of breed. So nobody wants to give that up. We want to make sure that it works in these environments, okay? So we need to move from an example where your application is long running. We all used to press the button, starts up, and it takes and then it's up and running and it runs forever, right? We're all used to those sorts of application design. That's what we were, trained to do. In it for the long haul, runs forever. But actually, now we need those small things. How quickly can you get started? I'm doing microservices, I'm doing all these sorts of designs where things don't live for long, and I have lots of them, and they have to scale. Totally different environment. But we need both of those. So if you've been doing Java for any length of time, you will have seen Java benchmarks. And Java benchmarks have a particular pattern, and I'll show you in a second. And that pattern has these heaps and things in it, okay? And that's great, but actually it's not the right profile. What our new world wants is a different profile. But we have to keep both profiles because we have the old workload, okay? We want all sorts of different profiles, but there's a basic pattern to them. So if you look at a benchmark, they tend to have this sort of curve. So the red line is throughput. How long does it take for your application or your benchmark to get to the point where it's servicing the maximum number of requests? And that's the red line. It takes time. A consequence of getting there is that you use up memory. Yes? And memory, in most of these benchmarks, tends to follow the throughput usage as you'd expect, but there tends to be some sort of bump. Right? So that can be because there's jittered code or there's more stuff in the heap and that needs to be Java garbage collected at some point, but it's around, okay? Bear that in mind. So let's talk about the profiles and what Java profiles need to look like. So let's do sort of a real example. So you've created a system and you get a workload. We don't get workloads that look like that. We get workloads that look like that. Demand comes in and goes, right? Sometimes it's predictable. Mostly it's not predictable. Maybe you can say Friday mornings it goes up and Sunday afternoons it goes down. But you get a pattern, okay? So how do you deal with that? How do you design your application? What do you stage it on? Well, if you're doing on-prem, if you're looking after this machine stuff yourself, you've bought a big box. And that big box, or very big box, or cluster, is designed to deal with the largest amount of capacity or workload that you're going to need, because you can't buy any more, because where is it, right? And that's cool. That's what you did. Now, you move that application to the cloud, and you have a different picture. Suddenly, you start looking at what you've bought that you're not using. So everything above that line, that red, is wasted money. Yes, it's wasted compute power, but it's now wasted money. So your accountant, if they're really technically savvy, will spot that. Mostly they're going to be going, hey, you bought this really, really big Amazon tier, or multiple Amazon tiers, and it says you're not using it very much. Do something about it, okay? So what do? Well, we break our application into small pieces. Yep. Small units. Small units fit under the curve just a little bit better. Less wasted memory. And of course, if you go far enough, hey, what is this? Any idea? Okay, so this is microservices. The only reason that we are doing microservices is because of this. This demand, which resolves into smaller units to allow you to scale and be economic in the cloud, is driving all our activities towards continuous delivery, microservices, microprofile, all these things come from that fundamental. Now there's more, because once you realize that you've got this, then you can start to imagine new shapes of application. You know you can have 24/7 availability. You've got cloud. You've got a different story. So continuous delivery, etc. Those become even more exciting for us because we have to do it quicker. But fundamentally, the drive comes from that economics. Okay? So, go back to that profile. Pick any one of those little boxes, and unless you do something magical, the profile for that little microservice is still the same. It takes time to get to the point where you are dealing with workload, yes? But now, with economics involved, cloud economics, suddenly you've got more costs that you could deal with. So the longer it takes for your application to get to the point where it's dealing with full workload, this line here, that means you've got another one of these hanging around that's dealing with that workload. Because the workload comes in, somebody has to deal with it. If it's not this, it's some other one. So there's a cost there. And if you've gone over this peak of memory, you may have had to buy an extra tier up just to get your application to start, and then use memory you don't need anymore. Yes? So that's more money. So what you want is this shape. Yeah? You want as fast as starting as possible, no peaks of memory. Okay? That's what you're looking for. Oh, and by the way, you want it now, because we promise cloud to everybody. Okay? So, that's the new pressures on us, and it's a challenge. The reason it's a challenge is we don't work that fast. The Java community is quite slow in delivering. And you know that because you've seen some of the things that have been happening. This is why so much of what's happening right now in the Java space is happening. Okay? So we're now trying to readjust our ecosystem. All these people or vendors are getting together to figure out how to do business, how to develop faster. Okay? So the new release cadence, it's about getting stuff out the door faster so you can build on it. Right? It's about trying to get more people involved in the community, more open source technologies, because if we don't have multiple starting points for these conversations about what the Java of the future looks like, we're all betting on one place, and that's not good. So we need more stuff. There's a whole bunch of stuff coming in OpenJDK, right? Cool stuff, right? Different implementations. So microprofile, evolution of EE. Let's take EE, figure out what it should look like for the cloud. Let's work together to create that. We have a whole bunch of implementations being open sourced so that you can try it and we have a place to evolve, okay? There's now 2 VMs out there that you can go use to get different characteristics, okay? And on the JVM side, there's a whole bunch of stuff we're doing which is about how to meet those new demands. Okay? What do you do when you've got situations where you haven't got time to do the full rope load jitting because the service that you're running is short-lived? So one of the things we're thinking about is, how do we do the jitting up front? Can we share the jitting? Can we find new ways of doing GCs? These are all being explored by these demands. And they're paying off. So this pattern here, okay, so take your favorite OpenJDK 9 with hotspot, basic benchmark. There's the throughput line, real data. So if I give you OpenJDK 9 with OpenJ9, so that's the J9 that IBM contributed to Eclipse, just switch. Faster startup. The space between the red and the blue line is more work done by your application just by switching VMs. Okay? And if you get really serious about it and you need enormously fast startup, you can get things like this. So this is you don't get the throughput in this model, but you get the startup. This is OpenJ9 with some AOT models, okay? This is where we are, but everybody else is working on this. So we have a lead, which is great, and you can benefit from this because it's OpenJ9, it's open source. You can go to adopt and download it, okay? And you can go to adopt and pick OpenJDK, your version of 8, 9, 10, 11, whatever, hotspot, OpenJ9. You can download them, play with them. It's all being done by the community, okay? And it's not just me saying, hey, you should use this IBM thing, the Eclipse thing. Other people are doing that. So you can use this and you will get the benefit personally, but you can see we're doing that because of the fact that it's driven by this cloud economics. It's really important for us to have demonstrations that we can do this with Java. Okay. So a bunch of words, but basically we went, well, we've got two choices. We can sit back and have our proprietary fantastic VM that you could benefit with if you gave us loads of money, and see the Java community suffer, or we can go, no. It's much better that we put all this stuff in one place and we start sharing it, because at the end of the day, VMs don't make money. VMs enable this Java community, enable all of you guys to do things that make money, and eventually the guys at the bottom get paid, okay? We need to do it together. So that's why we've done that, and it's available to you now. But it didn't stop there. Cloud turns out to be reasonably okay to achieve. It's a challenge for sure, but it's sort of business as usual. Different profiling, different heuristics, but it's still the same sort of workloads. Okay? That's not a big change for us. So you know how to do that. The big change is what comes after this. So who here has done any data analytics? Okay. How many of you have done data analytics using Java? Wow, that's different. Okay. Anybody here done machine learning? Machine learning with Java? No, it's not good. No, okay. Okay, and there's more to come.
Python.
Huh? Python, yes. Shh. So, why do I care? Why do we care? These are new workloads. Okay, they may not be new workloads, but they are new workloads, and they have a forefront. We know machine learning and AI and all this stuff is bubbling up. Okay, so what do we do to get that into the Java space? What do we do to get your hands on that? Well, it's going to be interesting. Okay, the future. Well, it starts here. It's still driven by economics, though. Nothing changes. The problem for us is that it's a new way of thinking. The thing about AI is that you train these things to do these jobs, and the jobs they're doing are ones that we as human beings aren't very good at doing ourselves. Okay? We can't internalize, visualize. It's difficult. Our brains don't work that way. Our brains are really good at doing standard computing. We seem to be okay able to do that. Okay? But we're getting these big pressures now to deal with these new types of workload which we can't keep in our heads. Okay? So it's all about optimization. How do I get an AI to do what it's supposed to be doing? How do I do data analytics? How do I do machine learning efficiently, right, without spending large amounts of money at it? Okay. How do I use these things to visualize what I'm doing? Because I have no idea what this thing is doing and it doesn't work, and how do I debug it, and brain hurts and stuff like that, okay? How do I get meaning for enormous amounts of data? These are all things that we're not very good at, and it turns out that pretty much most of our existing computer architectures aren't very good at it either, because they've been designed for this different sort of workload, okay? So let's take machine learning example. It helps you find some answer. Machine learning mostly is something that we train, not always, okay? But it's actually quite hard to be sure that you get the right answer. But the scale is so enormous. So here's an example. Let's do this as a thought experiment, okay? So you're going to hold a dinner party, and you're going to rearrange the people who come to the dinner party so that they each have the best conversation. You decide what best is, okay? It's your rules. You train it, but you say, okay, I want to have the best conversation. These 3 people, or 4 people, or 10 people, whatever it is, okay? When they're around the table, they're going to be organized so they can all say that was the best conversation ever, okay? So when you have 2 or 3 people, it's easy. Well, 2 people, it's a conversation. 3 people, it's a triangle. They talk to each other. That's a no-brainer, isn't it? What if you have 10 people around a table and you want to organize it so they have the best conversation? How many combinations are there for 10 people? Quite a few. So you imagine writing some code. We all write nice exhaustive code that could go through those loops, okay? Okay, so what happens if we take, I don't know, a reasonable sized conference room, bigger than this one, 150 people. What are the combinations of 150 people that you would have to seek to find the best conversation? Quite a bit. Okay? It's just, enormous. Machine learning helps you find a solution that is reasonably optimal. No guarantee it's the best, because to be the best, you would have to do all combinations, okay? But it's that's coming down the pipe to us. Yes, that level of complexity. And we already have people creating systems that do amazing things. And as Java developers, this is your new world. This is what's coming down the pipe to you. Okay? You read these things and you go, I have no idea how to do that. Systems that identify their own inefficiencies and address them automatically in real time. How do you do that? Right? Tailor responses to the personalities of your customers without meeting them and without upsetting them. How do you do that? Right? Uncover patterns, resources, trends, competitive advantages, invisible to competitors. How do you do that? Right? But these are all things that you are going to get involved in. You will be creating systems or helping these systems to be created. Okay? Mostly machine learning works by us human beings helping it learn. Right? We have these, you've probably heard about bias and how when you train things, a human being gets involved. Okay? It takes a large amount of effort for machine learning solutions to be built. Okay? So bear with me. The reason I mention this is because of what that means to us. So machine learning you see so often now people offering AI solutions, all sorts of data services that find insights into things. The challenge is that because it's so hard to do, we'll end up with this new world coming down the pipe. Lots of black box services. You created a service that you spent millions of dollars on and trained. You are not going to let that run anywhere else other than service in your cloud. Because if you give it away, you give away the training and the data. That's just too risky. So it's going to stay there. And people who use it, you guys, if you consume it, it's sticky, okay? Wherever you use it, you're likely to be bought in. So people want you to, they'll store it on Amazon and you go use it on Amazon. They'll store it on Google, you'll go use it on Google. okay, but you won't be moving off. Okay, you as developers are going to be spending more time figuring out how to get these services that exist on the cloud connected to your systems. How do you get your data to them? How do you get data back? That's your new world. Okay, that's what's coming. And of course, if you're really lucky, you'll be building these systems yourself. So the consequence of that is, number one, JVMs. JVMs of the future have to be able to do good machine learning. They have to be able to facilitate data analytics. It is an imperative that we make that happen. Okay? And you as individuals will be spending more of your time trying to figure out how you get data into shapes that you can get into these services. It's a different way of thinking. And of course, you'll be learning new stuff. So let's try and make this real. Let's talk about how this happens. Here's a word search. So you know how this works. There's a nice grid. Excuse me. Open this. There's a bunch of words. Ta-da! And those words are hidden in this word grid. So they're hidden vertically. They go down, they go left, they go right, they go at diagonals, forwards and backwards, okay? Right. So as a Java programmer, what would you do to find a small number of words in a word grid? So if I said to you, find me the word that's not on that list, that's not in here, okay? You write code like this. You go, okay, for every string on the list, I will go through left, right, da, da, da. You know how to scan it, right? You just, easy. You know how to do that. Almost intuitively as a programmer, you'd know how to write that code. And you come up with this, and you'd say, yeah, I figured out which word's not in there. I know the position, the direction. Yeah, easy. And you probably wrote code like this. No. You've never written code like that? Okay. Okay, so you tend to do that because it's easy just to go code, 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 okay? And then when you run it, the first thing you find is it doesn't run very well because it's only using one of your CPUs, because you've got 4 or whatever. And so, okay, that's not very good. So then you start to think about driving it from using data rather than code. So what you could do is start to think of that grid as a single sequence of characters rather than a grid. And then you can use int streams. Int streams give you numbers between some range. And then you can take that number, do a bit of modular arithmetic, and suddenly you've got the x, y coordinates. And you do that, and suddenly you've used your 4 things, okay? Just by starting to think about manipulating the data, okay? Still got some rubbish code that we need to deal with, okay? And again, you can deal with that. When you're searching through these word grids, you're probably dealing with the edges, you know, because the word might not actually be fully realized, might fall off the end. You might have Jav rather than Java. So you have to write all these boundary conditions. That's where all the code comes from. But if you think about it, you could change your data. You can put buffers around the outside. The buffer could be the width of whatever the longest word is. And then your code will never fall off the end because it will never find a complete word that runs out into here. So now you can make your code easier, okay? That's great. And when you're doing this direction seeking, rather than have lots of if, this, else, or case statements, you can think about directions as being data. Up, down, left, right could be an array of just basically, for this position add 0 to x, for this position add 1 to x, okay? Really straightforward. And then if you put those things together, suddenly you have a lot less code. Okay? Think simply by thinking about the problem differently and thinking about manipulating the data. And that's what the new world is all about, is about you making that translation from being coders to being data experts. Took time. I don't know why. Okay. But that's not good enough because there are other options to other things here. Okay, so that's silly. That was a silly example. But what happens when you've got billions and billions of grids? What happens if the grid's stupidly big, multi-dimensional, because that's what AI does. I give you a list that's super long, okay, or the word is so long. Being German speakers used to long words. Put those on the buffer's too big, costs too much money. That's real life, okay? So what do? What's next in your list as Java programmers to learn? This stuff. Hadoop. Apache Spark. Anybody use this stuff? Hadoop. Okay, so these are tools to help you do data analysis. This is where you start thinking about breaking your grid into smaller parts and having a cluster that's going to do the analysis. We want to make that happen. Okay. Unfortunately, that makes you think about it, is if you just break your data into sections and give one to each of these little nodes, the boundaries between these sections might be a problem because the word might split across the boundary. Now you've given half the word to one and half to the other. That's not a great thing. So you might do something silly, like you might break the grid into tiny parts and then do map reduce type things. All new techniques that you probably haven't spent much time with, but are going to be coming down the pipe for you to use because that's what we need you to do. And it gets worse. Okay? Because at the back of these wonderful compute things with clusters, you're expecting CPUs. Who knows what CPU is? Who's got 1, 2, 4, 10, 50? Okay. How many of you have got one of these, a GPU? How many of you have got a GPU that's not in your desktop? Oh, excellent. More hands. Okay. What about these things? Anybody got FPGAs or ASICs? Anyone know what they are? Nobody cares? Okay. So this is basically programmable hardware. This is take your problem and turn it into silicon. This is a programmable hardware. This one is you basically set it in silicon, and this one is programmable. But they're all out there, okay? The point is, here's the beginnings. These things are turning up in data centers, and so the VM has got to figure out how to get those into your hands as a Java programmer, okay? Unfortunately, they just don't work the way you expect. So if you've never programmed a GPU, then you're in for a treat, okay? Because GPUs do not work the way you expect. If you're writing Java code, and don't worry about the Java code, but you're writing Java code and you have threads, you're quite used to the fact that Java code in threads executes however it wants, and you have to do synchronization between them if you want to share data, okay? So you're quite used to that programming model. GPUs don't do that. GPUs have one execution control. Every single thread, and bear in mind it's a GPU, so there are millions and billions of these threads, they can only do the same thing at the same time. So if your code has different paths, switch statements, selection, stuff like that, then you will go down all the different paths in sequence. Okay? So it means that if you don't make your code data-driven, like my example at the beginning, you don't get the benefits, you get all the negative elements. Okay? So here's what's happening, is the next thing that you guys are going to have to learn is how to deal with applications that are data-driven, because it's the only way that we can get that on the VM. Okay? Because if you don't use it right, well, here's my analogy. Right? It's not like driving a car. It's like driving a car backwards. Right? Hey, that works. If you get it right, though, you get it right, you get enormous benefits. So OpenJ9, again as an example, has got built-in capacity for a tiny amount of GPU exploitation. If you've got a GPU at the back, then we can make use of it. And we can do sorts using GPUs, we can do other things, and we make use of the GPU, we get enormous benefits. That's what people are looking for. Get it wrong, and you get exactly the opposite effect of you end up spending a large amount of time in there. Okay. So, here's where really things begin to change dramatically, right? This is almost at your door. You write Java code, and what you actually do is you write a model of your application, and your JVM takes that Java code and converts it into machine code, optimized machine code for the platform of choice. So we can take your Java code and convert it into GPU code. That's not difficult. But we can't fix any of the application design elements that you have that means it will work poorly on a GPU. So the next step for you will be thinking about how you program GPUs in Java in such a way that you actually get performant on the VMs. Okay. So this is what's coming down the pipe. You're going to have these GPUs. They're going to make you think differently. The AI is going to make you think differently. The way that you've got these machine learning, you've got to get them connected. They're all going to make you work differently and think differently. And when I say GPUs, what does it look like? So NVIDIA's latest GPU, okay, stuck in the back of machines in data centers. These things are now being used by supercomputers. IBM's recent supercomputer, 100,000 nodes, all have these. So millions and millions and millions and millions of GPU threads. Okay. 2 petaflops, 412 gigabytes, 10 kilowatts. It weighs 160 kilograms. Okay? Which is the same as a panda. So you're not going to have one of those in your laptop, but you're definitely going to have one of those in your data center. Okay? And they're growing and growing and growing. That's why in the VM space, you're seeing things like value types turn up. Okay, because for us to get to GPUs, we've got to get over this wall that we built, this separation, this J and I stuff, right? We're trying to figure out how to take the object layouts that you use inside a VM and rearrange them into a flat space so that we can share memory very efficiently. It's really hard to take all that stuff, marshal it all up into a state and give it to a C program or a Python program because it doesn't know anything about Java object layouts, so we have to create our new ones. Right? And that's what's happening. Okay? So that's what the VM's doing in that space. GPU exploitation, better memory layout, things like value types are all there to help us get outside the VM. Okay? Make use of this stuff. And then, carrying on the machine learning thing, what about when you don't know what words you're searching for? How do you find words in here if you don't know what words are? Okay, well, you can go get a big dictionary and say, okay, I want to scan that big dictionary in this list. Well, yeah, but there might be words in here that are misspelt. Could you find those? So what do? You teach a neural net. Anybody written neural nets? Yeah, yeah, maybe a little bit. Okay, right. So what you do is you teach a neural network how words are constructed. And then you let it find them. Okay? You go, what? How does that work? That can't possibly work. Well, it does. It's so successful. What's this? Some headers. Okay? See copyright headers. Yes? What about this? Some C code? Yeah, comment, stuff, hash, Mac. Okay, I mean, you're not C programmers, but C code. Yeah? This and the previous page were generated by a neural network. A neural network was given access to basically GitHub, and it was taught what a programming language would look like, and then they ran it in reverse and said, generate something. And that's what it did, including the fact that you needed to have a header at the front. So it internalized that and created that. Wow. New ways of thinking. Right, so neural nets are number crunchers at the end of the day, and GPUs are great for doing neural networks. So another reason that we're trying to get Java connected efficiently with GPUs is so that you can do more machine learning and not be stuck with having to use Python. Okay, unless you're Python programmers. Okay. Okay. And then what comes after GPUs? Hey, there's more stuff. Who's got a neuromorphic processor? Who knows what a neuromorphic processor is? Okay, I do. Okay. Here's a neuromorphic processor. It's about this big. It is a computer designed to mimic the human brain. It is laid out like neurons. It fires like neurons. It's event-driven, right? It's real. It uses a fraction, absolute fraction of the power that modern data centers use, computer use. Okay, so soon as this is production ready, this will be going into data centers on the cloud, because this is going to be fantastic for neural networks, right? But you can't use one of those by taking your existing programs and shove it down there. It's a completely different design. And as soon as it's feasible for us to get to that from a JVM, guess what we're going to have a go at, right? All these technologies are out there. These Java technologies and non-Java technologies are out there for you to learn, but you've probably not paid much attention to them because it's not your day job. But your day job is changing. And if you're not becoming more up to date with machine learning and data analytics, you're going to miss out. The VM is something that we can modify to do this, right? Because JVMs are really good at taking models of application and turning machine code. And as soon as the hardware turns up, we're going to have a go. But the problem is you're the ones that have to change the way you design code, because we can't take your code as is and move it to these new architectures because they're not the same. Okay, and what about beyond neuromorphic processors? Is your brain full up? Okay, well, there was this nice guy called Lou Grover, and he came up with this idea. He said, you know those search algorithms that we've got, and you know there's this thing that says it will take evaluations. If you're searching for something, the rules of physics says it will take at least so long to search the list. Okay, and that's a rule. And he went, I can fix that, and I can make it, the blue line, much cheaper. And people said, fine, what do you want? And he said, well, several of these. These are called qubits. Anybody heard of a quantum computer? Anybody got a quantum computer? Okay. Quantum computers use bits that are called qubits because it's a quantum computer, but they're not on-off. They're on-ish and off-ish and everything in between, and they have angles and rotation. Okay. They look a little bit like this. They are enormous. Well, how big are they? Like a car, right? They are real. They're being used in production. They are rare. This is all supercooled conduits to get microwaves down to the processor. I'll show you a picture in a sec. We'll talk about what it does in a minute. So the schematic is something like that with all the wires. What you see is cryo, cryo, cryo. This thing operates just above absolute zero. It takes days, apparently, to get the room where this is in to a fit state warm enough for human beings to go in, and then days to get it cool enough. So it's not going to be in a data center near you soon, but that doesn't mean that it's not on the cloud, okay? Inside, you have hardware quantum computer, little qubits, and all these little microwave things, because you can't touch it, because if you touch it, then it collapses and you get an answer. You have to sort of talk to it gently, whisper, okay? And so when you take that and apply it to something like our search algorithm, qubit and Schrodinger's cat, so this isn't really how it works, but it's the best I can give you to give you an example of how it sort of potentially works. I have conversations with people, quantum computing scientists and ambassadors and all sorts of people, and I walk away going, yeah, I've got it. And then 30 seconds later, it's like, no, I didn't get it. Okay? So in your word search, what you do with a quantum computer is you just pick a space and go, is Java there? And the quantum computer would say, no. But you might just be able to see a reddish circle. It will give you some feedback that says, well, it might be a bit over there. So you try again. Okay? And it says, no. Try again. Okay? And you go on. Okay? And eventually, you get to something that might not be exactly what you're looking for, but it's close. So you don't get the Javas here, you get Javas in that region. Okay? Really quickly. and then you can then use traditional programming to do what you need to do. Okay, you can go play with one of these now. Quantum computer, research ibm.com/IBM, real ones. Now let me tell you, qubits, the number of qubits you get isn't very many. I think this is about 16. Okay, 50 qubits, which is about where we are right now. 50 qubits is the same amount of computing power as the biggest supercomputers we've got. 60 qubits, which is what we're almost at, is the same compute power as every single piece of computing in the world today. So when that stuff turns up, it's going to be interesting. This is graphical. There's a graphical tool. You can go play with it now. They're real. You can go use a real quantum computer online right now and play with it. You set up a problem, and then you apply constraints, and then you ask it the answer, and it says ish, and then you ask it again, and it says better-ish, right? And that's basically what you do. It is mind-blowing, and I have no idea how to program it. It's just wow. Okay. It's going to solve a bunch of problems that we can't solve today because it can cut through that time. It can do simulations. It's going to break cryptographic solutions. So yeah, all your nice 256-bit, 124, 4096-bit encryption, yeah, it'll be broken. The good news is you can get quantum encryption that is by definition is unbreakable eventually. Okay. But the main thing is the way that you're going to deal with it is different because you're going to do it data. You're going to be doing data-driven things again. Okay. Right. We just don't know how to get the JVM connected to it. But as soon as we can. Okay. So we're doing this, all of this, because the JVM is the best place to do this. Because we've invested so much in the technology, we've solved a whole bunch of hard problems. Right. Nothing comes close. This is the answer to us. All these activities, whether it's Hotspot or OpenJ9 or some new VMs, we have learned so much, and you're going to come with us to do that. Okay. The challenge isn't so much about the VM technology. There's lots of challenges. The biggest challenge is you. Right. The challenge is the future for you as a Java programmer. Microprofile, Jakarta EE, Spring, that's all cool stuff. But the next stuff that's coming down the line is more like this. The next stuff is more about data-driven, machine learning, AI, those sorts of things, and that needs you to change. And as the program models evolve, you're going to find yourself having to deal with things in ways that you weren't expecting. Okay? We've done all this, and we're still doing it. Right? We have all the best tech. Wow. So, what can I say? We have all these great ideas. We have great technologies. Some of it is being implemented right now. Some of it is coming. And no doubt there are new ideas coming along the right. Okay? Right? The point is, we're taking Java to places. We're taking the VM to places that we never imagined at the beginning. When Java was created on a toaster, all those years ago, pre-internet, it was designed for a really tiny device. And we've taken that design and that spec and we've expanded it. We can now run on tiny cards, to the biggest computers, to enormous clusters, to cloud, to supercomputers. We can get it to run on GPUs. We can get it to run on FPGAs. We can do that. And that's what we're going to do all the time that it makes sense and the economics drive us. The challenge really is whether you're going to come with us. Because the challenge is, as a Java programmer, you're changing from this old way of doing programming, traditional way of doing programming, existing way of doing programming, for this new model. So the quicker you start getting your head around machine learning and data analytics, the better it will be for you, because it'll help your career, but also it's something we need to start getting feedback from as to, hey, I want the JVM to do this, right? Because we're all in it together. As I said, the JVM is rising to the challenge. Are you? And that's it. Thank you. Thank you for listening. Any questions? You're all stunned silence? Okay. Hey, I've given you 5 minutes back. Thank you very much.